Okay, welcome back. Today we're wrapping up our section on processes. And what we're going to do today is not really talk any about more system calls. You have everything you need to actually create a simple shell processor, a command line processor. So today we're kind of bring it together. I'll give you some tips on the string processing part of it, which is probably going to be one of the harder parts if you haven't done a lot of string processing in C. It's a little annoying. I'll review whatever you'd like me to review on pipes and redirection. I'll go over them quickly, and then we can go into more detail on these parts. And I'll just show you generally the high-level algorithm for the shell, for a shell program. And then I've posted the next project, which is creating a shell called MySH. Similar to last semester, but not identical. It's not the same, not the exact same project. The inputs and outputs, things are a bit different. I've simplified things in some ways, made things more sophisticated in other ways. But I'll go over that as well during the class, the specifics of this project. So today, the file system project is due, my copy project. So that's due today. And remember, if you only have, it's not completely complete, then you can always resubmit for a small late penalty up until the last final project deadline. You're probably all wondering about the midterm. We'll have midterm review on Monday. It's just going to be taken from homework and projects. You can use the lectures to help you study, but I'll give you like a detailed list of topics that'll be on the exam. I haven't actually written it yet, so I can't tell you exactly what's going to be on it, but I'm just going to literally go through the homeworks, go through the projects, and use the lecture notes to help make an exam out of that. So if you've been doing the homework, following along with lectures, doing the projects, you should be fine. So we're going to cover everything up until processes in the exam. And then since I always get the question, the final will be cumulative, but it'll be disproportionately on the compiler stuff. Just for anyone who didn't read the syllabus, it'll be in person, but we're going to take it on web courses in person. So bring your laptop, charge your laptop. Let me know ahead of time. You can send me a private message on EdStem if you'd prefer doing a paper exam. It's much easier to grade an online exam. You can't imagine how long it takes just to flip 290 pages in an exam, which is what we had to do last semester. It takes like an hour just to flip pages and check people in. So it'll be in person in this room for the midterm, but it'll be on web courses. So if you have a device that can access web courses, you can take the exam on web courses. But you need to be here, and so we'll use the attendance system to validate that you're here. Now, some people, if you're in SAS, I'll upload, or you actually could just go to SAS to take the exam. It'll be on web courses. Let me know again if you'd prefer a paper exam, and I'll give one to SAS. Also, let me know if you need to do a makeup exam. If you have some good reason why you can't make the day, I'll make a makeup version of the exam. So you won't be able to take the exam off-site or at a different date. It'll be a different exam. I have to just make multiple exams if you need to do a makeup exam. So let me know if you need to do a makeup exam. Let me know if you want a paper exam. But I'm trying not to bring more than 30 paper exams, 50 paper exams. But I'll bring some just in case. Your laptop might die or you might have connectivity issues. So I'll bring some paper exams as well. As I said, this is where the materials are drawn from. There's not going to be any huge surprises. It's going to be drawn from the class material that I've already gone over. We'll do a review. You can bring notes, 8 double-sided pages. I have to limit it somehow. When I first did this, students would literally print out 100 pages, which was a bit excessive. So 8 double-sided pages. That means 16 total sides, 8 total pages. Don't bring a magnifying glass or use any tricks where you try to minimize the size of it. Reasonably sized, I'm going to use that legalistic term. I guess I'm the arbiter of what reasonable is in this. But I think most of you have a similar notion of what reasonable looks like. So that'll be the midterm. Questions about the midterm? Yeah. It's going to be a mix. So there'll be multiple choice, short answer, and open-ended. It'll be a mix of them. Yeah. No, they don't. You can print them out. This is computing after all. Yeah.
Can we write our notes on 2 different layers with 2 different
I didn't think of that. Yeah, and then, well, do you need special equipment to view it? No, I mean to view it. Like, do you need special glasses to filter out the light? Okay, I've never heard that technique. Yeah, I guess you could do that. I'd like to see that if you try that. I'd like to see if you can actually read. Yeah, I guess that should be doable. Yeah. Show me an example. I'm curious. Are you really going to do that? Okay. Show it to me. I'm curious how that will look. Yeah, so no special equipment, no special optics or electronics to view your notes, unless you actually, have a recognized need for that equipment. Other questions on the midterm? Yeah.
You said of the processes, but that includes processes, right?
Yes, up to and including. So everything from before the midterm review, including today. So everything, including today. But, the process stuff, we've spent a lot of time on the process stuff, so and lots of repetition. So hopefully, the basic stuff is there, like what's the difference between a process and a program? What's the syscall for creating a process? What's exec versus fork? All right, other questions on midterm? Yeah. I don't know yet. As I said, I haven't actually made it yet. I haven't made it yet. So I think, I don't know, it'll be something like, let's see, you'll have about an hour. So I don't know, 3 minutes per question on average. So there'll be a bunch of shorter ones and then a bunch of long. You'll have to do coding on paper, without the help, or not on paper, but on in an editor without the help of your compiler. So yeah, and also, so when you're using web courses, that's the only thing that should be open on your machine. So we'll have proctors walking around, leave your cell phones off, don't cheat. That this is the golden rule. You shouldn't need to cheat. You have notes. There's been lots of repetition if you follow the homework. Yeah. The practice problems would be like the homework and the projects. Those are the practice problems, and all the coding exercises in class. So I'm literally just going to draw them from there. So not exactly, but they'll be the same concepts. I'm not going to do extra concepts that we haven't covered in class. So if you've done all the homework and you can do all the projects and you can do them with notes without extra Googling or homework answer websites, then you'll be fine. You'll be fine. Other questions on the midterm? All right, questions on the FS project since it is due today? Yeah. Sorry, saying. Oh yeah. Just do 0644 for the permissions on writing, as I showed in class. I didn't cover that too deeply. This is just the read, write, execute permissions in the Unix system. Just use 0644. Other questions on FS? Okay, let's do the homework. So hopefully it's getting a little redundant and easy. Why doesn't a program have to open the standard in file? Yeah, it's provided by the parent process. So the convention in the Unix world is that when a process is forked, it's forked with standard I/O. And which file descriptors are standard I/O? Yeah, 0, 1, and 2. I saw a hand gesture. I'll take that answer. 0, 1, and 2. There's also, macros and constant variable names for that. And so what I said, what files comprise standard I/O? That's in, out, and error. Write a bash command that uses ls -l and grep, defined lines matching RW. So this is just another using the pipe with the command line. So ls-l, this gives you a listing of files with additional metadata about the files. This is the permissions. So this is where this 0644 is represented. And then we just pipe it to grep. And what do we give to grep? Because we want to match the string RW, we just give RW to grep. And it'll filter out all the ones that have RW. So this is a less interesting example because all of them are in there. Is anything not writable? Questions on that? Questions on that exercise? Okay, and then write a snippet of code that creates a pipe between two processes and redirects the first one's standard out, my spelling there, to the second one's standard in. Use any programs to run that you like. Questions on this? So we covered this last time when we did piping. So the answer is basically in the lecture notes. So this is the pseudocode for it. And just to quickly review piping again, you create the pipe. You just call the pipe syscall. What gets returned by the pipe syscall? Two file descriptors. These are here in the array that you pass in. You pass the array, which is a reference, and pipe will populate that array with two new file descriptors that represent two new open files. One is the write end of the pipe, one is the read end of the pipe. They're writing to the same in-memory buffer. Then you fork the left child, and in the branch that will be taken by the child, you redirect the output. Questions on this call here? We're taking the right end of the pipe and using that to replace what the standard out file number is. Standard out file number is 1 file descriptor, and we're replacing file descriptor 1 with the right end of the pipe. Questions on that? And then finally, we run the left program, the program on the left of the pipe. Because we already set up I/O, we called fork, we created the process, but we didn't start running the program. We set up the I/O between the fork and the exec, and then once we call exec, then the find program will be running, or whatever program we gave. Questions on that? And then same thing for the right child. So for the branch taken when you're in the parent, branch from the fork taken in the parent, we do nothing and just continue on to fork a new process for the right child, the right process child of the pipe. First thing we do, what we do here is that we overwrite the standard in using the read end of the pipe. So we replace the read end of the pipe file descriptor, use that to replace the standard in, which is file descriptor 0. And same thing, we exec the write process. Once we're back in the parent, we can just call wait to wait for both children to finish. And that's it. That's how you answer question 4 here. Questions on this? Yeah. No, just the parent will exit, and the two processes, I think, should just continue running. We'll use this in our shell. We'll wait because we want to be able to. So just like when we run bash, if we're running a long-running bash program, bash is still running in the background while this program is running, and we don't see a new prompt until that program exits. So we'll use that in our shell program to wait for the commands that we executed to finish, and then once they finish, we'll come back and present the prompt again for the user to insert new commands. So that's why that's one reason why you'd want to use wait. If you're writing a server and you're forking off processes to handle incoming web requests, then you don't want to terminate. You want to wait for those processes to finish so that you can continue on making new processes after that. All right, questions on homework? Piping, redirection, process creation, file I/O. Yeah. Yeah.
In the parent, I guess, since those processes, inside the main file, with ls, and then I guess, does this program, the main, the master process, know that those two processes are running?
Does it know they're running?
Yeah.
Indirectly it knows they're running because it executed them. Is that what you're asking? So I think, the wait is actually kind of that's the communication that you have with the kernel. Now you could take the PID, so you have the process ID in the parent. So you get the process ID. So you could ask the system whether these processes are running, if that makes sense. So it's not, actually all processes know which other processes are running in the system. So the parent can also know. And it'll know indirectly because it'll have to wait for them, or it can use the process ID to check whether they're running. I mean, they could exit. So here, technically, they could exit, and this wait would be like pointless. But yeah, there are ways to tell whether the children are still running. Other questions on processes? On FS project? Okay, let's go over shells, command line shells, how they work, the algorithm, how we can implement them. So hopefully you know by now, using the command line yourself for the projects in this class, is that the command line interpreter executes commands. Given the program name, it will go out and fork a new process and exec that program for you. And these commands also take arguments, which are space-delimited, more or less space-delimited tokens or strings that are given after the program name. And where do those arguments end up? How do those arguments get to your program? What's that? Actually, no. So the standard in is a file. So these are just a string that's given to the command line shell. Yeah. That's right, argv. So these end up in argv. So the command line processor is what takes those, parses these out into an array, and passes them to argv. If you recall when we did, let's look at the pipes example here. When we had a call to exec, you see that exec took the path to the program, and it also took argv. So it was the parent process that passed argv to the process. And this is really designed around command line processing, because this is actually part of the syscall. The command line processor will take those and populate an array with them and pass them to exec, so that the program will have them to main. You can think of exec as indirectly like a call to the main method of your program. So if you've ever wondered why you don't just like write code in your C file, you put it in a special function. Well, outside of the system, that main is just another function. It's just another function call. Just by convention, that function is the entry point to your program. And also by convention, the system will pass in an array of arguments. Now those arguments can come from anywhere, but when it comes to writing a command line processor, the convention is that we pass these on the command line with the name of the argument. Questions on that? Questions on how a command line, or what the command line looks like when you run a command? So this is true for all the commands you run in this class. So if you run GCC and say like, I think I have a program in here. If we're compiling a C program, all of this is the name of the program. So this is the name of an executable program. And all of these are just command line arguments that are passed via argv to the GCC program's main method. So once the process, so all the command line shell does is it looks at this program name, and all the rest of these strings on the command line are effectively just given to the program. Bash doesn't really care what these are. The program determines the meaning of these arguments. Bash just passes them along to the program. Questions on that? Yeah.
How does it process like flags and
It's the same thing. It's just a string, right? It's just ASCII codes. It's just strings. So the bash, the command line processor doesn't really care whether this is a minus or a plus. The use of the hyphen is just a convention in these Unix tools. And it's just a convention that all of these command line tools use. But you don't have to use that convention. You could use plus, you could use no symbols at all, you could just use any string you want. But there's just a convention of how these arguments, the style of these arguments. You can actually read this in, let me see where, I think that's the command line one. Yeah, there's even a C library function called getOpt for getOption, which parses command line, parses these arguments for you, parses the use of dash. But it's just a convention. There's nothing in the bash shell processor that cares about what the style of arguments that you pass. To the shell processor, this is just a sequence of strings that gets passed to main. And it's up to the program to ascribe meaning to those arguments. Other questions on this? Yeah. Oh, so they get passed to argv. So if you've ever wondered why you have argv and where it comes from the exec call. The exec call is what passes argv. And the system, you transition to the kernel space, the system will take this array and it will ultimately pass it to your main method in your program. So that when you're creating a new process, creating a new running program, this is where argv comes from. It comes from the call to exec. Yeah?
So for any regular shell, the shell fills in the full path because when you call like GTC, it's not.
Yes. Yeah, that's a good question. I only covered this very briefly, but so this other part, which I also didn't talk about much, but if you read the book, you'll see it. There's also this environment, which is kind of like a database of key value pairs. It's just a bunch of variables and settings, and these are kind of like persistent state for the shell and for processes. And when you log in and you start up bash, a series of setup scripts, whenever you log in, will assign this path environment variable, and that path environment variable, just by convention, contains a bunch of delimited paths. And so when you type the name of a program, bash or whatever shell processor you have will search through each of these paths to find a program named GCC. And I'll actually show you another variation of exec VP, which will do that path lookup for you. So you won't have to do this on your own. You can just use exec VP, and it will just work. It will do the path lookup for you. So I have this somewhere either in the I think it's in the project description. So if you use this variation of the exec, I think P for path, it will do this path lookup for you. So you won't have to worry about that. You can just, as long as you give a program, just like bash, whatever works in bash should work in your shell by using this variation of the exec call. Okay, so that's command line execution, and you'll see the mechanics of this when you actually write your processor. But let me go into more examples here. Okay, so there are some commands, and I won't make you do this in the project, but there are some commands that are so-called built-in commands, like exit and change directory, and these are not programs. So the which command. The which command will do this path search for you and just tell you the full path of the program. So it's sort of showing you kind of internally what bash does, or the system does in order to find the program. But notice that CD, there is no program called CD. So what does CD do? CD changes the directory. So why is there no program to do this? Why is it something that the bash interpreter has to process on its own? Why is it built in?
It's already built in. It's like a function that's built in.
Yeah, you can think of it like that. The reason is that what it does is it changes the working directory. The working directory is associated with the process itself. So if we had another program called change directory, it would just change the directory of that process, not the bash process. So if we want to change the bash process's own working directory, it needs to call chdir within its own program, within the bash running program itself. So anyway, there are built-in commands as well in bash. You can see these documented in the man bash page. There's like a huge set of these commands somewhere. So they're documented in here somewhere. I think they're called built-ins. Where are they? Yeah, so if you're interested in, this is a long documentation. So yeah, here's the huge number of built-in commands, including CD here, that the bash processor just runs on its own. It doesn't call another program to do that. You can't tell just by looking at the command which it is because they have the same syntax. You just give the name of some operation here on the command line, and whether it's a bash built-in versus a program that runs, you can't tell just by looking at it. You'd have to look at bash's documentation to see that there's a bunch of built-in commands. So for instance, I think there's a time. Is there a time command? Well, anyway, yeah. So that's the built-in commands. All right, here's the basic algorithm for your shell processor, a bash-like shell processor. You just loop forever, basically. You loop forever, reading in the command, and then running the command. And you do this over and over and over until there's no more input, or say an exit is made. In our project, we'll just use end of file. We'll just use empty input to signify that we're done with commands. But this is the basic loop. You just loop forever, reading in the next line, run whatever program was given by the user, wait for that process to finish, and then repeat. So that's the basic command loop. So here's the basic algorithm for processing the commands. We'll take the commands, which are just a string. There's no meaning to them. They're just ASCII. It's just a text file. We'll break it up into its pieces, which you can call tokenization or parsing. We'll create a new process, just like we did in process creation. Set up any I/O redirection that the user asked for, and then execute that command, and then wait for it to finish. And once it's finished, we'll go back to waiting for the next input. Questions on that? That's just like the basic command line shell processing algorithm. Pretty short, right? You just loop forever, read in line by line. Once you read in a line, break it up into its pieces, take the program name, create a new process for it, do any redirection you need to, and then run that program, and repeat. Questions on that? So the high-level algorithm is fairly straightforward. As usual, especially in C, the details are the tricky part. God is in the details here. All right, so let me start kind of at a high level what processing these commands looks like. Okay, so let's say we've got this command given to us to our shell. And in C, what you're going to get is you're just going to get a string. And these are spaces in your string. With me so far? You just get a string. So independent of the command line processor, these are just ASCII codes. Did you guys learn about ASCII? Okay, yeah, this is just ASCII. They're just they're just numeric conventions for our Roman alphabet. And in C, it's just a character array, a string. So your command line processor is going to ascribe meaning to this. It's going to give meaning to this string by interpreting what it's supposed to mean. And so we have, we hopefully know the command line convention now that the first white space delimited string is the name of a program, and the rest are the arguments to the program. So what we need to do in our C program is to break up the string into its tokens. And so you can do that by just separating tokens by white space. And there's some C library tools you can use to do that. I'll show you an example later in the class. But the first thing we'll do is we'll break up the command into a sequence of substrings, a sequence of tokens. You all learned about string processing, right, in like CS1, CS2. Hopefully it was like a big topic, right? Also, if you do programming interviews, often you'll get like string processing stuff because it's just so kind of tedious and tricky to get right. But this is the first thing the command processor will do. It'll break up the string into its pieces. And by convention, we use white space to break those up, like spaces, tabs. So with me on this so far? Questions on this? So we get this whole string as input, we break it up into its pieces. And now we look at these pieces of the input, and we take whatever is the first, and this, think of this as an array. So if this is an array of 3 elements, an array of strings, so an array of characters, then the first element is going to be the name of the program that we run. So this is what we pass to, this is what we're going to pass to exec. And use VP so that we don't have to do path processing. And then the rest of this array, this is what we're going to pass to exec for argv. So you pass this also to exec VP as the argv parameter. Questions on that? Does it seem pretty straightforward? Maybe? I hope. So for just running a single program, that's all you need to do. Take the string that was given to you, so you'll just literally read from standard in, which is what bash does. You'll read from standard in a string that the user gives you. So the user will type this on the command line. This is going to standard in, so you'll just get it from standard library string reading stuff. Like, I'll show you this, but you can use getS. Have you used getS before? fgetS? No? Okay, so you can read in a string from standard in. There's a system, not a system call, but a library call. You can read this string in, and then you have this string in memory in the C program. The first thing you do is you break it up into its into its tokens, tokenized by white space. And once you have this array of strings, you just take the first one and use that as the program for exec VP, and take the rest of it, take that array, and use that as argv. Questions on this? So one little wrinkle we'll see in the code is that the convention is that argv, the exec call, doesn't have argc. It doesn't list the number, the size of argv. So you just make sure the last element is null, and then exec VP will work correctly. Questions on this? Okay. All right, so to do that, it's actually pretty straightforward, and I really suggest that you start with just a program that does that. And if you can get that done, then you're like halfway there. You're well on your way to writing this command line processor. But it's pretty straightforward. I mean, it's literally just taking the fork exec program that I gave you and adding some string tokenization. So to make this a little bit more realistic, we're also going to have redirection and piping in our shell. So you'll process the inputs for the same symbols we use in Bash for redirection and piping. This will start getting a little bit trickier. So I've simplified the syntax of this a little bit to make processing easier. Those details are in the project description. But let's take an example of doing redirection with our command line processor. Bash does something more flexible than this, but we're going to do something simpler for our project. So the way this is going to work is the last argument is going to have a angle bracket that will tell you whether it's redirecting input or output. So let me show you what this looks like with our command processing. So we do the same thing. This comes in to your program via standard in as a string. We do the same tokenization that we did before. And so I've given to you as a requirement for the shell that there should be no space here. And this is really just to make the parsing easier. So you can assume that there's no space here. So another way to look at this is that this is just another argument, but if its first character is an angle bracket, then it's a redirection. If it's not, then it's one of the arguments. And it'll always be at the end of the command. It'll always be one of the last arguments. So that'll just make the string processing easier. Doing the full processing is really parsing. We're going to learn about that in compilers. But this will make the string processing a little easier. All right, so if one of your tokens in your input is prefixed with either greater than or less than, then use that to do a redirection to a file before running the program. So this may be index 0, this is index 1. So just like before, this is the program name that you pass to exec VP. And when you're processing the input, once you encounter a string that indicates a redirection, then this is not an argument. So this is not an argument to ls. Instead, this tells you to do a redirection. And so how do we do redirection? How does redirection work? Or what are the syscalls we use for redirection? Dupe. What's that? Duplicate. Well, you don't need piping for it. So piping is between programs. But yes, dupe for this. So what you'll do is you'll check, is this a greater than sign? If it is, then you save, you check for the greater than sign and save this substring. And that's pretty straightforward, right? Instead of starting here in the array, you start here. And you take this, open it, and then just like we saw in redirection, after you fork, you use dupe2 to overwrite the standard out file num with that FD. Does that make sense? Questions on this? Yeah.
Sorry, this might be a little off topic, but I don't understand at this point. What is the difference between that line right there, output the output of OS into the input of that next command, and just putting a pipe there?
Oh, so this isn't a command. This is a file. So this work, yeah. So yeah. So this is like the way Bash works as well. So if I say ls, I mean, actually, you don't have to put spaces either. If I say ls pipe it to out.txt, it's going to have the file out.txt.
And you couldn't do that if that was a command on the right hand.
Well, so this is what your Bash processor, your command line processor is ascribing meaning to what this is. So in Bash, if we have an angle bracket, even if you put a program name here, Bash is still going to create a file with that name. That's the difference between piping and redirection. Redirection goes to a file on disk or a file that you can name, and piping. So piping just has different syntax. You use the vertical bar to pipe it. I'll show a pipe example as well. But this is this kind of starts getting into compilers because it shows you that this string has no intrinsic meaning. It's your interpreter or your language processing tool that gives meaning to this. So that question about, well, why is this not a program? It's just because it's defined that way by the interpreter. Now, you could write a new interpreter and use different syntax and say, well, this means pipe. You could do that because there's nothing intrinsic about this ASCII symbol meaning pipe. It's all the processor that we use, the bash processor. And so your shell, I've just defined for you the requirements of the shell, and this will indicate, this just indicates open this file under this name and use dupe to redirect the output of this program here. Does that make sense? That makes more sense, right? So this is kind of a little entree into the compiler section, which is a little more wind warping because you have to kind of separate the meaning of symbols from just the symbols themselves. Yeah.
So are you using standard out F2 or FE?
Sorry, this is file no. I ran out of space, so I just put ... Look at the real example there's an example of redirection. This is the constant for file descriptor 1. Yeah.
I guess one question for like the FS project, for example.
Yeah.
When we passed in when we did the command copy and then like 2 arguments.
Yeah.
We had 3 arguments.
Oh, okay. That's a good question. So why does argv have 3 elements? Oh yeah, sorry. And I actually, you're right. I made a little mistake here. So argv is actually this. So sorry about that. I led you astray. So argv is actually this whole thing. So just by convention, the program gets the entire command line, including the name of the program. And this is useful for automatic documentation, or it's useful to have this for some programs, to have the name that it was run under. The path will also be here. So sorry, a little mistake. So this is the program name, but argv, just by convention, has the entire array, the entire tokenized array. Sorry about that. Yeah.
So then normally by default, we will know that argv at 0 index.
Yes. That's right. That's right.
We pass the exit.
What's that?
And we would pass that.
Yes, you pass this array. The point. Actually, it's the pointer to this first element. You pass this array to exec VP. And so, yeah, sorry for that oversight. You can see that here, where the program name is this path, and I could have just put prog here to make it a little cleaner. But you can see argv contains the program name and the argument to the program. So this is why, like in FS, when you have 2 arguments, argv has 3 elements. It has 3 elements because it includes the name of the program as the first element. So yeah, good question, and I made a little mistake here. So this is what argv is, the entire array. Questions on this? Yeah.
So in this process, is argc also kind of set?
So exec does not take argc. Instead, it takes a null delimited array. So you just have to ensure that the last element of argv is null. And then I think the C runtime or something in the machinery from exec to main will compute the size of this and pass that as argc. I think it's probably the C runtime that does it. But the exec command, you don't need to pass the size. Instead, you just make sure your array is null delimited. The last element is null. So these are sort of the minutia, the minor details that you definitely have to get right. But you have some example code here to start with. So I would just start with having just like a program, no arguments, get that working. Then try having a program with various numbers of arguments, 1, 2, many. Get that working. And then gradually build up. So this is the kind of incremental style of development where you make sure the program works for the simpler case before you move on. So make sure it works with a single program with no arguments, make sure it works with 1 argument and then many arguments, then move on to doing redirection and piping. So this is not part of RB. Okay, let me show an example that has both command line arguments and redirection. So by convention in this command line processor, the redirections are always at the end. They won't be mixing the arguments and the redirection, which I think is also true in Bash. So we may have a command like this. So you can use the same tokenization to split up the command. So this is the program name. This is argv, and make sure that you've got a null at the end. And this will be used for open and dupe2. That makes sense? So there's the full example. So this will I also ask you to support redirecting input, and you should be able to have both input and output redirection. So there'll just be some like case checking. You'll check, okay, do I have a redirection? Then open and dupe2. Otherwise, you don't need to do open and dupe2. Or you can do open and dupe2 to standard out. Questions on this? So no space here. Assume no space here. That'll just make parsing easier. And these will always be at the end, in any order at the end, but they'll always be after the arguments. Okay, and also to further increase the realism of this assignment, we'll also support piping. So for instance, we take a command like this. Again, the pipe symbol has no intrinsic meaning. It's just an ASCII code for pipe. But we'll do the same thing for the processing. We'll just tokenize the input by white space. So make sure that you do have space around the pipe so that it can be tokenized. That's not required in Bash, but it's a simplification for our shell. And so what will happen here is a little different. So now you'll do the same command line processing for the left and right arguments. It can take, or left and right programs. It can take arguments. It can take redirection. Each one can take arguments and redirection. But let me start like simple. So you'll do in this blue box, you'll do the same thing that you did for a process up here. You'll do the exact same processing you do here to create the program. But when you have a pipe, you'll also set up piping. You'll also call pipe. You'll have to call pipe ahead of time, just like we did in the pipe example. And use redirection on each to redirect the output of LS to the input of WC. So you're basically cobbling together all of the little code examples we had for redirection and piping and organizing it all together into a command line processor. Questions? Other questions on this? Yeah.
I'm sorry for getting this.
No, go ahead.
Could you explain the difference again between redirection and piping?
Sure. Yeah. So let me show a piping example first, and I'll use this example. So in this case, LS and WC, they're programs. The interpretation of this is that they are programs to run. So each of these will have a fork and exec to run them. But before we do that, we'll call pipe to create this nice Super Mario Brothers colored pipe. Pipe will create this in-memory buffer like we talked about last time with pipes. And then your shell will call fork and then dupe2 to redirect the output of ls to this pipe, and then call exec to actually run ls. WC will be similar. We'll call fork, we'll call dupe2 to redirect the input from the pipe to WC, and then finally call exec on WC. So that's piping. Piping involves running multiple processes for each element in the pipe. I'm only going to ask you to have a single pipe, so you'll be running 2 programs if you see a pipe. And each of those programs will have their out and in redirected to each other, to the pipe. File redirection, in contrast, like ls out.txt, instead, what happens here is that we have a single process. So we'll call open to open out.txt. We'll call fork to create a new process for ls, and then dupe2 to redirect standard out of ls to out.txt. So it's just changing standard out to a different file, whereas piping, it changes standard out to be the pipe file and runs another process and changes its standard in to be the pipe. And then, we finally call exec ls. So the big difference is that there's a single child process being created here for ls, and we redirect to a file. We open a file and redirect to it with dupe2. And here we create 2 processes and redirect their standard out and standard in respectively to the pipe. Does that answer your question? Other questions on this? Yeah.
Purposes of the project coming up, does that mean for piping, if we're going to take in 3 arguments and the second one's going to be a pipe, meanwhile the redirection between part of the second argument?
It's going to be a little more tricky than that. So let me show like the full example. Well, first let me show one example and ask what you think this might mean. So let's say I have an example like this where I say ls, redirect the output to out.txt, pipe to WC. What does this mean, or what should it mean? Or does it mean anything? Yeah.
So we're calling ls redirecting its output to out.txt.
Yeah.
And then while redirecting its standard out from standard out to out.txt. And then piping standard out from ls, which is now out.txt.
Yeah, so I see your discomfort. So something's a little wrong here because we're asking our shell processor to redirect the output to 2 different places. We're saying redirect it to a file, but also pipe it to WC. So you don't have to support this. This is just going to be prohibited. It's going to be an error in our shell processor. With Bash, it'll just, what's that? Yes, it's undefined behavior. Well, you have to check for it and then just quit. Oh, I see. Okay, yeah, depends on what you mean by undefined behavior. So, yeah, I mean, you could argue that undefined behavior, if you don't check for it, it's defined. But it's defined to be bad behavior, I guess. I don't know. I already made the project to say you check for it. So it's not, well, you mean undefined behavior as in like, you can do anything you want or I won't check for it. I already wrote the project script. Well, you think it'll be easier?
Yeah, because then you don't check for it.
Oh yeah, okay. Ask on that stem and people can vote on it, see if they really want to take it out. I don't have to check for it. It's not a big thing, but I just wanted to cover all bases. What's that?
It was kind of a joke.
Okay. So check for it. Check for it then. So, I mean, it is kind of, well, it actually, I think in Bash what'll happen is this will just be waiting for input. I'm actually not sure. We can check what actually happens in Bash. Yeah, so it's just, oh no, it actually runs. So WC just gets no input. So the redirection seems to take precedence. So it does redirect it, and then there's nothing left over for word count. So, but you don't have to support this. Just check for it, issue an error. Okay, so you won't, yeah, and same thing with in. So if you redirect the input of the right side of the pipe, yeah, you don't have to support that. Okay, so let me show, like, full example, the most complicated type of command you'll have to process. So I'll just do a single argument. Single argument and multiple arguments will be very similar, but let me give myself enough space here. Okay, so this illustrates all the features that your command line processor should support all at once. So remember, this is just a big string that comes in the input, so you get this big C string. Then tokenize. So tokenize all of the elements of this string. So this is what your tokenized input should look like. So remember, no spaces between the angle bracket and the file so that it's just easier to process. Yeah?
For the project, should we support like multiple pipes?
No, you don't have to. You can just do a single pipe. Multiple pipes would be a fun bonus project as part of a bonus project. It alone may not be a bonus project, but yeah, it's fun to figure out that algorithm to do that. But you only need to do a single pipe. Okay, so we've got 2 programs to run. So here is the first program to run. Here is the second program to run. And within here, we have the program name, and we have argv, and we have the redirection. So I'll just call this dupe2, or yeah, redirection with dupe2. And similarly, we have another program, another argv. Remember that this should be null terminated. And we have the redirection. And then between these 2 programs, we also have a pipe. And this pipe will cause a redirection of standard out of the first program to the pipe and standard in of the second program from the pipe. Questions on this? There's like the full support of the program. Yeah.
So, I guess the pipe would be the LS program and the WC program, and then obviously LS takes the input from input.
Uh-huh.
And
Yeah.
all that LS and WC pass the pipe and outputs the out.
Yeah. Yeah. Yeah.
Do we have to worry about permissions like if we use sudo?
Well, sudo's a program, so it actually should be supported. It actually should work if you use sudo, because sudo is just a program, so you can just run it, and its arguments is the command you want to run, and then sudo will then use a syscall to invoke that process.
Wow, I thought it was just like a bash.
No, yeah, it's like a program. So it's literally a program here in bin. So yeah, that's sort of the magic of the Unix style is that it makes that kind of thing possible, where you can sort of create new systems and new commands just using fork, exec, and redirection. All right, questions on this project? So this is basically describing the project. The details are in the project description. Yeah.
Will you give us all the things that we'll test? Not as in like every technique, but just descriptions?
Yeah, I'll give you a description. I'll do like what I did for the FS project, where I'll give you half the project. This is sort of my compromise in trying to figure out how to give you tests without, just giving you all the tests. So you should write your own tests, but I'll describe what I'm going to test at least, and then give you half of them. It'll be just like FS. I haven't put the tests up yet. I haven't made tests yet, but they'll be up soon. Okay, so we went over all this. Let me show you now how to do string processing. So I'm going to give you a bunch of the code for string processing because it is kind of a pain. But not everything. So you'll have to kind of manage the arrays yourself, figure out where the program names are. You'll have to do all that kind of semantic implementation yourself. But I've given you code for the syntax part, actually processing the string. There's a library tool called string toke, part of the standard C library, which will tokenize the input according to a delimiter. So that's the call down here. So we're taking the input, and tokenizing it by white space, by a single space. So I'm not going to test you on anything besides a single space. So let me go through this code. Create a new space for the buffer. Ooh, and I forgot to do free for that buffer. So there's probably a bunch of memory leaks in here. I wasn't super careful about that. But we create a new space for the input size. There's a maximum size that I've given you in the project description. And then here's our command line prompt. We just print out money sign, space. So money sign followed by space. And we're going to use this tool called fgetS. fgetS will read a string until a new line character from whatever input you give it. So we're going to read from whatever file you ask for into a string buffer. So fgetS will read from standard in. This is the file we're reading from, and it'll read 1024 bytes into this buffer. Questions on that? It's just a wrapper around read. You did read already, so this is just a useful wrapper around read. If there's no more input, which you can signal with Control-D, then you exit. So, this code is given to you. Have some debugging output here, doing a little processing to remove the new line, which is given in there. So if the command is empty, you don't do anything. You just continue. You go to you put the prompt out again and ask for input. And here is an example of using string toke and actually getting some information here. So string toke is like destructive. So I copy it because it might be useful to keep that string around. So I copy it with malloc and string ncopy. So this is probably a little. Well, let me know let me know on EdStem or here if you have any questions about what this looks like. But I'm copying it while I'm tokenizing it. So this is the new string this is the copy of the string. When you call string toke the first time, it gives you the first token in the string, and then you just repeatedly call string toke on null to get the next ones. It's a little bit of a wild interface to string toke. You can only be tokenizing one thing at a time, but that's the interface to it. So that's why I've given you this code, because it's a little painful to work with. And so then I just have debugging. So this code will take our input buffer and it'll tokenize it by white space and just print out each of the tokens. With me so far on this, more or less? All right, let's run this. And let's see if it works. Okay, so there's our command line prompt. That's what printf does. So you have something like this in Bash. It just literally prints, the command line shell. It kind of invents this command line shell for you by just like reading and writing ASCII characters. So if we type in nothing, if we hit enter, we get it's a one element buffer because it has the new line character. But once we remove that new line character, it has a length of 0. So in that case, we just continue in the loop. We don't do any processing. If I've put a single string to tokenize, it will call string toke and start printing out each of the tokens. If I put one of my commands from the example, it'll print out all those tokens, and so on. So I can put our full example here. Oops, I don't have that facility. So you can see here's each token, just like I showed in the diagram with string toke. Questions on this? Yeah. Sorry, change what? Yeah, you'll store them. So use your new skills from CS1 and CS2 to make a data structure to store these elements so that you can then do this interpretation according to the semantics of the Bash processor language. Okay, so that's string processing. There was something else I wanted to show. I can't remember though. So yeah, that's string processing. Oh yeah, the homework. So let me show you the new homework, which is relevant here. So I've asked you to write an example program that tokenizes a string by spaces, so you already have that, but stores it in some data structure. So for homework, I'm asking you to do that step. So take this program that I've given you and create a data structure for yourself that will store this sequence of tokens so that you can then start doing processing on it. So you can start pulling out the program name, the arguments, redirections, piping. So have that all set up for yourself. That way, the rest of the project, you can just focus on implementing the behavior, and you don't have to worry about string processing anymore. Get that out of the way. And then I strongly recommend starting with just single program name, no arguments, then doing single program name, one argument, then many, then do redirection, then do piping, and so on. All right, questions? Questions before we conclude? Yeah. Oh, yeah. Sorry. Yeah.
So in these cases where people pull like a space in the time and the problem
Do you get what? Yeah, I know what you're saying. Yeah.
So do you handle that?
No, you don't have to handle that. Yeah. It'll be easier if you just have the no space. All right, everyone. Have a good week and weekend.